Yeah, hello everyone. So, as mentioned, my name is Hiram Rayo Torres Rodriguez, and I'm a senior embedded AI research engineer at NXP Semiconductors, and today I'll be talking about how to leverage neural architecture search for computer vision at the edge. So let's get started. Yeah. So, as some of you may know, efficiently deploying AI models on embedded devices can be very challenging. And one of the reasons why this is the case is because hardware deployment is typically not considered when designing these AI models. So when one wishes to pick a model from the wild and then eventually run it on a chip, given that there's quite a lot of options of chips that one can pick from, one of the problems that one may encounter is that one can see suboptimal real-time performance or the model simply not fitting on device, which is kind of like the worst case, right? Because then this means that this simply is a showstopper. And this typically actually happens even after applying common neural network optimization techniques like quantization and pruning. So one of the questions that one may ask themselves at that point is, well, what to do when these quote-unquote common optimization techniques like quantization and pruning are actually not sufficient? And this is where neural architecture search, or NAS for short, comes into the picture because, well, NAS is a more advanced optimization technique that aims to derive highly efficient edge-ready models automatically. And the way in which this is accomplished is by performing an optimization that targets multiple objectives. So on the one hand, NAS would maximize the task performance. So for example, the accuracy or the precision in the case of object detection, for instance, while at the same time minimizing a hardware-related metric, like think about model size, real-time latency, or energy, to ultimately find a highly optimized solution. And this is done by considering deployment aspects during the search optimization procedure, like for instance, the efficiency of the quantized operators, with the idea being that if I perform NAS to derive a highly optimized model, this model will typically be really tailor-made to my particular hardware solution. So in this figure, then you see the traditional deployment flow. One starts from a baseline model. This model, we can also call it the seed network, and then run it on the target hardware, and typically achieve a performance that may not be the one that you're looking for. In this case, we exemplified with real-time latency. But in the NAS deployment flow, this would look a little bit differently. So one would pick up this model, then feed it into the NAS optimization procedure, and then NAS would derive a model that is tweaked in terms of its architectural properties, for example, the kernel size of the convolutional layers, and then run on the target hardware with the idea of the hardware then giving back feedback to the NAS procedure such that NAS can know what is the best setting that is ultimately best running on my particular chip to, as we mentioned, come up with a really tailor-made, highly optimal solution. And what I'd like to also mention is that these days, NAS has become the de facto approach for neural network design. So in this figure, you see here in the top left corner, the space of the highly performant neural network architectures. And these are all NAS-based networks, either done fully automatically or using NAS as its crucial enabler. So when it comes to neural network architecture design, which, as Jeff was mentioning this morning, is one of the biggest challenges when it comes to solving a particular application, this is the go-to solution these days. Well, I hope that with this, I've gotten your attention, because this seems quite nice, but of course, then the natural question is, well, how does this actually work?